Hey everybody. Alright, sorry y'all are going to have to bear with me. My tablet unrooted itself, and I left my USB cable at school, and since I'm home now, I'm just going to go ahead and record this using my cell phone as opposed to directly screen capturing from my tablet. So anyway, chapter 11, we are talking about sort of an introduction or the basics of enzyme catalysis. And this chapter is chapter 11. I kind of skip around a little bit in some of the sections, but most of the chapter is really good to read, so I would recommend reading the whole chapter. So here are our learning objectives for this chapter. Print this out, read over it before we continue with the lecture, so that you can keep these learning objectives in mind as we go through the material. So first off, what are enzymes? Well, enzymes are proteins that catalyze a reaction. They mediate nearly all the biochemical reactions in the cell, and they're able to catalyze or increase the rate of reactions by lowering the energy of activation for a reaction. So if we can decrease this energy of activation, our reactants can go through the reaction coordinate much sooner to become products. So as we can see here, this reaction is exergonic, meaning that the energy levels of the reactants are higher than the energy levels of the product. So we know this reaction is spontaneous in this direction, but because it has such a high energy of activation, i.e. our transition state is a much higher energy than both the reactants and the products, this reaction will occur very slowly or may not occur at all in order to overcome this energy barrier. But what enzymes can do is bring this energy barrier down so that at normal physiological conditions, this reaction will occur very quickly. So how do enzymes do that? Well, there's various mechanisms that we'll explore later of how enzymes can catalyze reactions. But basic to all enzymes, they utilize an arrangement of functional groups within an active site, which is the region where the enzyme catalysis occurs. So as you can see here, we have our substrate binds to the active site of our enzyme, and in this active site of our enzyme will be functional groups off amino acids that can help spur this reaction and help bring down that energy of activation barrier. So some properties of reactions governed by enzymes. They typically have higher reaction rates, so the reaction can occur much quicker. They can occur under milder reaction conditions, such as physiological conditions, which is, pH 7, low pressure, as well as mild temperature conditions, 37 degrees C. They have greater reaction specificity, so you don't get any side products or unrelated products. And they also provide a capacity for regulation. So we can block enzymes, or we can bind co-substrates to enzymes to help encourage more of the enzymatic reaction, or use inhibitors to block the enzymatic reaction. So the body can utilize these properties of enzymes in order to either spur reactions forward or halt reactions. There are 6 basic enzyme classifications, and they're usually termed based on the reaction that they catalyze. So you have oxidoreductases, which catalyze oxidation reduction reactions. You have transferases, which transfer functional groups. Hydrolases, which do hydrolysis reactions, so we're breaking covalent bonds with water. Lysases are group elimination to form double bonds. Isomerases perform isomerization reactions, so going from maybe the D to the L conformation in a chiral molecule. And then ligases do bond formation coupled with ATP hydrolysis. Okay, so if you think about ligases, I always think it's kind of gluing molecules together. So enzymes are specific. The active site usually has a geometric complementary to its substrate and often has electronic complementary too. A lot of times, we consider this the lock and key fit model. If we see here, you can see you kind of have like a square and a circle. And then in the enzyme, we see that there was perfectly a cleft that's like a square or a circle already formed. And so this is how we believed enzyme substrate interactions occurred for many years, but now recently X-ray studies have showed us that it may be more of an induced fit model, where the active site is largely preformed but undergoes some conformational changes upon binding. So it's sort of like putting your hand in a glove. The glove already sort of has, the shape of your hand. It's a little flat, but once you put your hand in it, it really conformationally changes and then fits you like a glove, right? So if we look at this, obviously the geometric complementary can be seen as the substrate goes into the enzyme. However, we can also see the electronic complements that's going on here. The enzyme has a positive charge functional group here, where the substrate has a negative charge functional group here. So we get that ionic interaction. We have hydrophobic interactions here and here. And then we get some hydrogen bonding interactions between the substrate and the enzyme here and here. Enzymes are stereospecific. This is primarily because enzymes themselves are chiral. Remember, all of the amino acids in nature are L amino acids. Therefore, they are stereospecific for their substrate as well. As you can see here, in this enzyme active site in our substrate, if the molecules were arranged any differently, if this was flipped or these guys were flipped, you would see that it would not be able to fit very specifically into the active site, because the active site is specific for this cone, cube, cylinder pattern in that specific stereo specificity. I know this is probably very disorienting recording this way, and I do apologize. Another thing to consider with enzymes is a lot of enzymes utilize cofactors, or molecules that enzymes require in order to function. Cofactors that happen to be organic are termed coenzymes, and you could have coenzymes that are transient. Those would be called co-substrates, so they only bind to the enzyme at the time of catalysis with the substrate. They're sometimes used during the co-substrate is often used up during the reaction, and so the co-substrate itself has to be regenerated between reactions. A prosthetic group is permanently bound to the coenzyme. Remember, we were talking about prosthetic group of heme with hemoglobin, and we said that heme is permanently a part of hemoglobin, and without the heme there, it would not function. The term apoenzyme describes the enzyme without its cofactor, which is therefore inactive. And the holoenzyme, which is the active enzyme with its cofactor. Okay, so again, remember I said unlike enzymes, cofactors must be regenerated, especially the transient cofactors such as co-substrates, because they get used up during the reaction. Prosthetic groups may not often get used up unless the metal cation that could be a part of the prosthetic group may have to be replenished. Another term to be familiar with is Zymogen. So Zymogens are proenzymes that are inactive precursors of enzymes. As you can see here, an example of that is trypsinogen, is this sequence at the N-terminus. Trypsinogen is a protease. If it was activated where it is produced in the pancreas, then it would damage the pancreas before it could be released into the stomach to digest protein. So often enzymes are produced as zymogens or proenzymes in the inactive form, and then transported to the site of where they need to be activated. And then once they're transported to that site, in this instance to the stomach, there's another enzyme present called enteropeptidase or trypsin that cleaves trypsinogen and makes the active form trypsin. So trypsin itself can cleave trypsinogen in to make it activated. So this is a self-feedback activator. So wherever you have trypsin, when trypsinogen gets transported to that area, such as the stomach, it can activate itself. Well, another molecule of trypsin will activate trypsinogen by cleaving between lysine, oops, I'm writing on the wrong screen, between lysine and isoleucine. All right, activation energy and transition states. So again, we're coming back to why enzymes work. So as you remember, enzymes work to catalyze reactions by bringing down the activation energy to help make the reaction go faster. So either one of these reactions are still spontaneous, but by bringing down the activation energy, we can speed up the reaction. Often this activation energy is reduced because the catalyst or the enzyme stabilizes what we call the transition state. So by stabilizing the transition state, it brings it down to a lower energy field so that we can get to it easier and then come down to the product. If we look at a very simple reaction where you have A goes to I, our transition state, into product, we see that really we come up with a two-step process. So we have our substrate, which will bind to our enzyme. The enzyme then helps form and stabilize the intermediate state, and then eventually our product forms and the product enzyme releases. So our intermediate or a transition state now becomes sort of a second part of this reaction coordinate. So instead of just being one reaction coordinate as we see here, the transition state energy level is so much lower, and now we have a two-step process. So one step, two-step. Okay, so we have product plus enzyme reacts to form the product transition state complex, which then further reacts to form our product releasing enzyme. Now often, now that we have two steps, step one and step two, we have to determine which is our rate determining step. So is the formation of the enzyme substrate complex, which yields our transition state with the enzyme complex, does that require more energy and therefore take longer than product formation? Or does the enzyme substrate complex formation to the intermediate take less time than the product formation and dissociation of the enzyme? And so often this can't be determined unless we do it experimentally. And when we do that, we determine our rate determining step, and usually it's the rate determining step or our slower step that determines the overall rate of the reaction, because the other step will either happen so much more quickly that it doesn't really affect the overall rate of the reaction. And this is going a little more into organic chemistry, if y'all can remember from discussing the differences between SN1, SN2 reactions based on the rate of the reaction. So remember I told you there's a number of different catalytic mechanisms. We can have acid-base catalysis. In this one, the transition state is stabilized through the donation or acceptance of protons to or from the substrate. You can also have covalent catalysis, where a covalent bond is actually formed between the enzyme and the substrate, stabilizing the transition state. Metal ion catalysis. In this one, enzymes utilize metal ions to bind the substrate, which can allow the substrate to become properly oriented. They can then mediate oxidation reduction reactions. And then often they are able to stabilize the transition state through electrostatic stabilization or by shielding negative charges. Proximity and orientation effects. In this mechanism, the enzyme is able to bring together two substrates within close proximity and orient them for proper reaction to occur. Often, the relative concentration of two substrates in the cell may be so low that without the enzyme present to bring them together, the probability of them coming close enough together in order to react would be very low. Also, you can have preferential binding of the transition state to the complex. So in this, the enzyme binds to the transition state of reaction with much greater affinity than the substrate or the product, again, therefore lowering the transition state's overall energy. So some quick examples of enzyme catalysis are proteases. So here we can look at 3 different proteases. We have chymotrypsin, trypsin, and elastase. And in all of them, you can see chymotrypsin cleaves proteins at phenylalanines, trypsin cleaves at lysines, while elastases cleave at valine. And you can see in their binding pockets or their binding sites that these binding pockets are developed specifically for the amino acid residues that they cleave at. For chymotrypsin, you have glycines, which allows the very bulky hydrophobic phenylalanine ring to come in. And then the serine is used as a nucleophile in order to cleave the bond. And we'll see that in more detail in a minute. Trypsin, again, it has a negatively charged aspartic acid residue to attract that positively charged amino group on lysine, as well as the glycines help make room for that bulky functional group, as well as some hydrophobic interactions with the lysine's acyl chain. In elastase, you have valine and therine that can help bring in the alanine functional group, the valine alanine's hydrophobic interactions, and then the therine's hydroxyl group can then be utilized as a nucleophile to help spur the cleavage of the cis bond. So the cis bond that you see here is where the actual breaking occurs, and that's usually at the peptide backbone between the amino acid we're cleaving and then the N+1 amino acid next door. So let's look at chymotrypsin's mechanism in a little more detail. Remember, it's going to cleave at phenylalanine. So if we look at the binding pocket of chymotrypsin, phenylalanine can come in and tuck its little hydrophobic aromatic ring into the cleft, which is then further stabilized by glycine. Serine, histidine, and aspartic, here, these are called your catalytic triad. This is a common mechanism found in what are called serine proteases, where here aspartic acid provides a hydrogen bond acceptor of histidine, of the imino off of histidine, which then puts more electron density on the nitrogen here, which can then pull the hydrogen off of serine, which then makes the oxygen off on the serine hydroxyl group a great nucleophile to come in and attack at the peptide backbone of the substrate's phenylalanine. So as you can see here, we have the serine hydroxyl group oxygen, after it lost its proton, is now covalently bound to the carbonyl carbon. This now very much negatively charged oxygen is being stabilized by the amine peptide, the alpha amino group on serine. as well as the hydrogen on the imina group of histidine 57, and then some stabilization from the glycine's peptide backbone as well. As you can see, the electrons on the peptide backbone at phenylalanine are going to move over to the nitrogen, which is going to cause these electrons on the oxygen to move over. And we see that we break the bond between the phenylalanine's peptide backbone and the next amino acid residue's peptide backbone. So now we got the substrate has been cleaved at the phenylalanine site. Okay. And then rearrangement reoccurs when serine 195 ends up getting its proton back through the cascade. Or actually, I think water comes in and donates a water, which then cleaves the covalent bond here. But we can look at that in a little more detail in class. And the book goes into a lot of detail on this reaction mechanism. But I just kind of wanted you to get an idea of how much is going on between functional groups and the enzyme substrates in the enzyme active site in the binding pocket. That some functional groups in the binding pocket are there to stabilize the substrate's transition states, while some functional groups in the active site are there to promote other functional groups to interact with the substrate itself. So it's usually often a very kind of complicated but beautiful cascading mechanism that we've seen repeated over and over already in a lot of our biochemistry lectures. I believe that's everything on this lecture. We will get together on Monday, do a little activity to hopefully reinforce. A lot of this lecture is just key terms, knowing, being able to compare and contrast the different mechanisms. Being able to, if I showed you a plot like this, could you tell me which step is the rate determining step based on which one has the higher or lower energy of activation? How do enzymes catalyze reactions? By stabilizing the transition state. And then again, some more key terms like zymogens and proenzymes, the different types of cofactors, stereospecificity, geometric specificity, the classifications of different enzymes, why the properties of reactions that are governed by enzymes, so how enzymes make their reactions sort of unique and ideal. And that's basically it. So we're back at our learning objectives. All right, so I'll see y'all Monday. Hope y'all have a great rest of your weekend.